Okay. All right. Let's get started. So there is an exam tonight. The official start time is 7:15. I'd like it if you would try to get there a little earlier, just so that people can come in and get a seat and the proctors can distribute their exams. Have a little time before the start time. The syllabus, if you haven't gotten it, does have the room assignments. I've had a couple of questions about what the abbreviations mean. K means Kedzie, Umberger, and then CW is Cardinal. So check the syllabus if you have questions. Try to do it ahead of time just so that you, of course, the syllabus is on Canvas under syllabus. Okay. All right, so we are going to push on today, and of course, today's lecture, like Tuesday's lecture, will not be on the exam this evening, but we are going to push forward and try to learn a little bit more about vector valued functions. And in particular, we want to know about the arc length. So we have a curve we're looking for, and this is section 3.3. If we have a curve, we're going to look for the length of a curve. Okay. So suppose we have a parametrized curve. C is parametrized by some R of t. And when I say that, I'm going to mean that it's, say, continuous and differentiable. Doesn't quite have to be differentiable, but it does have to be one-to-one. But differentiable makes it easy to say it's one-to-one by saying that, well, locally one-to-one. It's has a non-zero derivative everywhere. And so let's say it's parametrized by this vector value function R of t from A to B. In other words, t is in the range, or in the interval AB, closed interval AB. So then the length of C is given by the formula, which is an integral from A to B of the magnitude of R prime of t dt. So that's our, actually, that's our length. That's the length of a curve. Okay. Now, what's the explanation of this? So explanation, why is this true? We'll do a little problem in a second. Well, I mean, from a certain perspective, this is just saying, if you know your speed, right, for the entire trip, and you integrate your speed with respect to time, then you're going to get the total distance that you've gone. And so this explanation is just sort of a roundabout way of doing that, of explaining that. So this will be R of A, your initial point. You'll get to this point R of B. And the idea is, okay, well, you can partition this up. You can partition up your curve by partitioning up AB. So you have this interval AB, and you can partition it to A equaling A naught, less than A1, so on, all the way up to A sub n equaling B. And then this, so this will be R of A naught, this is R of A1, and so on, R of A2, until you get R of AN. And then what you can look for is you can say, okay, let's say I want to go from R of A1 to R of A2. Well, you're looking for sort of an approximation to this distance of the curve. So you can kind of build little piecewise approximations. all the way out, including here. And you can ask sort of what is the length of this approximation? Well, the idea is to say, I know how fast I'm going at this particular point in time, R of A, right? So how fast am I going? The speed I'm going at this point is going to be given by this R prime of A, 1. That's my speed. And then I can say, well, and then I know how much time elapsed when I start here and get there, namely like delta T, or if you want A2 minus A1. So if I think of it that way, I can say, sorry, let me just move this up here. I can say that this is this times delta, say A, okay? And that gives me a good approximation. It says, okay, well, I'm going this fast, and over a period of time, if that time is really short, I should make it about this far. And so this is approximately the length of this guy, this red. And so then if we sum up all of these approximate lengths, AI, delta, and maybe I should put an I here, delta AI, that this gives us a good approximation. So approximate, sorry. This is a good approximation to the length of the whole thing. And then the whole idea is, well, if we take the limit as these AIs get closer and closer together, if we take the limit, then what we're going to get by definition is the integral. And that will give us a precise value. So this particular formula is a version of what's later on we'll see is what's called a scalar line integral. So this is just the scalar line integral of the function 1. These, I want to say really clearly, these are very difficult to compute in general if you have a complicated function. And the reason for that is because you'll see in this expression, you've got this magnitude, which means there's a square root. And integrating functions that are all living under a square root is very difficult, if not completely impossible, at least in closed form. Of course, computers can do these types of approximations up to a high degree of precision, and therefore you can get values computationally using a computer. But if you want a closed form solution, you have to kind of start with a nice function. So let's do that. And again, I do want to mention, we're not, aside from talking about a scalar function or a vector valued function in higher dimensions and a curve in higher dimensions, this integral is not a multivariable integral, right? There's only one t here. We're integrating with respect to one variable. So this is just good old fashioned calculus once we take the magnitude. So let's see how that works. So let's find the length of the helix. R, oops, let me give myself room. R of t equaling, say, 4 cosine of t, 3t, 4 sine of t. From t, and of course I need to specify my a and b. So from t equaling 0 to 2 pi. Let's take a look at the solution. So we need to calculate this integral. Well, I guess it's in red here, this integral here. And before we calculate that integral, we need this function, which is the norm of the derivative, our velocity. So let's calculate the velocity first. This is easy. We can just take derivatives of each of the components. So derivative of cosine of t, negative 4 sine of t. Derivative of 3t is just 3. And derivative of sine, 4 sine of t is 4 cosine of t. Okay, that's great. So now we need to take the magnitude of this. And for that, we have to put everything under a square root. Whoa, not that. Sorry. And we're going to square everything and add it up. So we'll get 16 sine squared t plus 9 plus 16 cosine squared of t. But we can pull the 16 out of sine squared plus cosine squared. And of course, we know that sine squared plus cosine squared is 1. That's why doing this kind of a calculation for a helix is quite nice, because this is then just the square root of 25 or 5. And once we have that, our life is very good. We can just take the integral from 0 to 2 pi of 5 dt. Of course, hopefully everyone here feels comfortable doing. It's 5t from 2 pi to 0 or 10 pi. That's our length. This is length. Okay. So if you're given a problem, there's 2 things that could happen. It could be like this, or it could be really, really hard. If it's really, really hard, either you were given a bad problem or you made a mistake. Such things are possible. Okay, so that's great. We know how to find, at least in principle, we know how to find the length of a curve. But now what we want to do is actually, we would like to do something where we get sort of a unique parametrization up to sort of direction of a given curve. And that unique parametrization has a name. It's called arc length parametrization. And the reason you might want to do something like this is, especially if you are interested in physics, is you might want to be able to calculate, you might want to be interested in calculating curvatures of paths and things of that type, because such invariants of a curve do determine some of the physics of, well, of the motion of a particle, for example, or body in space or something. Okay. So our goal now is to parametrize or reparametrize a curve C at unit speed. I'm going to say it. This is just kind of intuitive language, let's say. So let's say I have a curve like this. So here's my curve C. And let's say it's given to us in with some parametrization. So there's some R of A here, and out here we get to R of B. Well, when you look up at the formula to compute length, we see that we need to calculate this magnitude. We need to calculate the speed of our parametrization. And if you're given an arbitrary parametrization, of course, you can be going, you know, slow here, speed up, slow down, speed up, and so on. And again, that kind of enters into some difficulties, not just for calculating length, but for calculating other things. So what you want to do is you want to say, well, there's one way I could uniquely go along this curve if I started here and ended here. And that is, I could drive like an old man, like you can drive like, I don't know, like an old person and go 1 mile an hour, right? I guess old people, that would be really slow. But okay, let's go 1 unit per unit time, okay? Length of 1 per unit time. And that will give you a unique way of traveling along this curve, right? It just you only can go at that speed. So your tangent vector will have to equal your velocity vector, or your unit tangent vector will equal your velocity vector at any point. So how do we do that? How do we do that? This is called arc length reparameterization. Okay. Well, we need to take some steps. So this is our goal. Let's take some steps. So step one. We're going to find something called the arc length function. Define arc length function. We know what it's going to be. What we know it's going to be is going to be the following thing. It's going to be some function, s of t. It's going to be a function s, which takes the domain a, b, and returns as a range equal to 0, L, where L is the length of the curve. So that we know, and we can define it in a second. And the formula, we have a formula for it. And that's based on what we just learned. At time t, this is the integral from a to t. Notice I'm putting the dependent parameter, the independent parameter, pardon me, up in the integrand as a bound for integration of r prime of t dt. Ooh, this is bad. I'm going to have to put a dummy variable in here because I don't want to mix my variable with my bound of integration. Let's call it u du. Okay. So what is this? What is this telling me? Okay, well, let's figure it out. Think of AB as the time on your watch. Okay, you start your journey along the curve at time A, you move along, and you end your journey along the curve at time B. Now, if you look at your watch at any point in time, say time t, you're, say, here. What is s of t going to return? S of t is going to say how far you've traveled. It's the length up to that point. That's what this function is doing. So when you're at time A, you haven't traveled at all. When you're at the end of your journey, you've gone all the length of the curve at an L. And in between, you get this mess as far as the formula goes. Clear? Good. Okay, so we have a function. And now what is our second step? Step 2. Step 2 is to go down memory lane. Memory lane. We recall something about this, something called like the derivative. Who can tell me about this? So I'll write it out. Hold on. Let's write this part out. I'll be fundamentally disappointed if you can't tell me about this. Oops. What can I say about this? And what should I use? I am fundamentally disappointed. Are people shy? Are you like inside, you're saying, I know this, but I don't want to embarrass my fellow students? I'm going to assume that. Okay, don't be shy. Anyone? Any suggestions? Cancel out. I appreciate the suggestion. Okay, there are these things in math. There are these things in math. They should be thought of as like, these great pillars, right? That, all of the, intellectual world is, or at least mathematical and science world are sort of built upon, right? So when we hit one of these wonderful pillars, we try to like decorate their theorem with this wonderful name, like the fundamental theorem. You have like the fundamental theorem of arithmetic this great Euclid's theorem. I know you all know that one. Even if you don't know, you know it. Fundamental theorem of algebra, I'd be surprised if many knew that. It's a very wonderful theorem. This one is the fundamental theorem of calculus. We're in calculus. Fundamental theorem of calculus. It says if you take an integral and up to a bound t, and then you differentiate that, you get back your integrand, your function, assuming your function is in any sense, well, basically integrable. So this, I think the student that said canceled out meant this, so that you'll get that. By the fundamental theorem of calculus, which there are sort of two statements. And it breaks my heart that I didn't hear a chorus of cries citing such theorem. That's okay, it's okay, my heart's been broken before. Yes, no, that's by inabilities to state theorems is what I'm saying. not in other ways. That's never happened to me. All right. What did I walk into? All right, so look, you've seen now this definition, or not this definition, this construction is something you've seen before, even if you've forgotten it. It's very useful to use fundamental theorem of calculus. I just want to note this. If you look back and you want to learn how you define the natural log of t, you'll see in high school they don't define it at all. Sometimes they define it. They define it as like an inverse to exponential function, but they don't ever give any good definition. This is also defined like this, right? This is the definition of the natural log. Then you prove it's actually an inverse to exponential function. But then, the fundamental theorem of calculus is, once you have this definition, that's why you see the derivative of natural log is 1 over t. It comes immediately from this definition. So this kind of thing is actually quite common. It's sort of baked into a lot of the things you do utilize in applications all the time. So why do we want to recall that? Well, what we can say, and what I said early on when I'm talking about good parameterizations, is I never want to stop. I don't want to stop in my parametrization. I want it to always kind of continue on. So this speed should be non-zero. I should never stop. So if we know we have a function that's always has a positive derivative, we remember then that s of t is increasing, strictly increasing. Strictly increasing. Okay. Strictly. Now, what do you know about strictly increasing functions? Well, they're increasing, sure. But you also know that they satisfy both tests, right? Of course, they're functions, so they satisfy some horizontal line tests. But they also satisfy our vertical line tests. But they also satisfy a horizontal line test, which means they have an inverse function. So there is an inverse function. Sometimes this function can be quite difficult to define. It can be very difficult to define or impossible with just standard techniques, but sometimes you can. So you have some inverse t of s. Okay. This is an inverse function. And we all know like how this looks. We have some increasing function from a to b. Say it goes like this. And then so this is t going to s of t. And if you want to find the inverse, you just flip this over the t equals s line, and you'll get some kind of thing. I don't know, I didn't draw it very well. Something like that. I guess it goes up a bit, sorry. So it goes A to B. And this is 0 to L. So the idea is you just take this picture and you kind of reflect, and you'll get the inverse function. This is a graph of the inverse function. So this is T of S. Okay, once you have an inverse function, we can remember another wonderful theorem. These are all things from one variable calculus, which is you have this inverse function theorem. And there is actually a multivariable version of the inverse function theorem, which we won't talk about in this course because we need a little more linear algebra than we have. But in one variable, it just says that if I take the derivative of the inverse function, t prime of s, it's actually just equal to 1 over the derivative at t of s at t of s. That we know. This is what the theorem says. Okay, this is the concludes the memory lane portion. This is all one variable calculus stuff. But the point is what we can do with this definition of the arc length function is there exists an inverse function satisfying this nice property. And once we know that, we can then go ahead and reparameterize. Final step. Take R of S. Well, by definition, they write this in the book R of S, which is not my favorite notation, but this is defined. This symbol here means this is defined to equal R of T of S. You take your usual R, vector value parametrization R, and you put in the function T of S that you just found when you found the inverse function. And this is going to be is arc length reparameterized. Your parameterization. Let's check. Let's check. What we need of this function is we need to have unit speed. That's what we need. This will still trace out the same space because T of S has range A to B. And so R of T of S is going to go from R of A to R of B. So we know it sketches out the same curve, but we need to check that it's unit length velocity or unit speed, if you will. So we take R prime of S and we apply the chain rule. This is going to equal T prime of S times R prime of S. And this looks silly because of the way they write R of S. R prime of S is really the derivative of this function. Okay, and then it makes this looks more sensible. So here, if you want, replace S with T of S in both of these cases. And then it looks like a chain rule. And this prime is really just a product. It's a scalar product. This is a vector, and this is a scalar. Okay, but we found from the inverse function theorem that this is 1 over S prime of T of S. Okay, and this is going to be R prime of S. But what is S prime of T of S? Do you remember? I take S prime of anything, I get this. So I will get 1 over S, I will get R prime of S, and then S prime is R prime of S. Again, S prime is R prime of T, but okay, when I write S there, I'm replace it with T of S. So you can see that this is a unit vector. I'm taking a vector and I'm dividing it by its norm, by its magnitude. So this is a unit vector. And life is good. We're done. This tells us that R prime of S is equal to 1. Okay, so that was fun. Let's do a problem. So I want to walk you through it so you're convinced at least that this makes sense. This procedure is not some mystery of like, the universe, you're given this thing to do this one thing, but you can see that there's actually some logic to it and it will solve the problem for you. The hard steps here are calculating the arc length function, which can be extremely difficult or impossible in closed form, and calculating the inverse function of the arc length function. So you have to be crafty in writing problems to make sure that such tasks are accomplishable. Such a word exists. So reparameterize R of t. Okay, so let's see if I was crafty enough. 1/2 t squared, t, 2 times the square root of 2 over 3, t to the 3 halves. And here, I want to reparameterize it by arc length for t between the values of 1 and 2. So this is my A and my B. Okay, well, we have to follow at least the prescriptive part of our steps where we define our arc length function, find the inverse, and then put the inverse function into our original parameterization. That last step might be kind of messy, so I don't know if I will do it or, well, we'll see. Okay. I should mention also, I said they're unique. If I have a curve, the arc length parameterization is unique if it's directed from one starting point to one end point. Of course, if it's a closed curve, you have to specify those start points and end points in the direction. If it's an open curve, you just have to specify the direction. Okay, so there is some choice there that you need to make. But usually if you're given a parametrization, that choice is there. All right. So first step, we want to find the arc length function. This is usually the hardest part of this type of a problem. So, well, I'm going to put this R, I use this dummy variable, U. Let's go back a second when we define this arc length function here. I use this dummy variable U. You want to do that. I want to say, really do that. I mean, you can use a different variable if you want, like V or something, but you don't want it mixed in with this. You're going to make a mistake if you mix these variables. The point is that when you integrate, you're going to integrate this variable away. It's going to go away at the end of the day anyway. So it doesn't really matter what label you put on it, what letter you use for it. So but you don't want to confuse it with the other variables that you have in play. So in that vein, I'll calculate R prime of U. And of course here, I'm just I put everything in U instead of T, and we'll see that we get U here, 1 here, and then here, well, I get a 3 halves. That will cancel out with the 2/3. So I'll get a square root of 2 times T to the 1/2. Square root of T if you want. How do people feel? Sorry? You, yes, I mean you, thank you. Thank you. Yeah, the choice of notation, I don't know, it reminds me of a story. You can really make mistakes choosing certain types of notation. So after I finished getting my PhD, I was giving a job talk at Northwestern, where I actually did get hired. But there's this category, which is a mathematical structure called the Fukaya category. And well, the notation I used for it which was common notation, wasn't my notation, was this. It was common notation. Everyone used it. Nowadays, people prefer this. But this, you put the space in here. And of course, I had an open set, and the common letters you use for open set was a U. And I gave this whole talk, and there was this Professor Ezra Getzler who was just sitting there, very famous guy, just giggling the whole time. And he came up and said, you know, you really should change the notation. So yeah, be careful with, I guess there are other considerations when you're choosing variables. All right, anyway, back to the calculation. So okay, so let me just write this. This is 1, and then I can put this as 2 over the screen. I know my value u is going to be between 1 and 2. Okay, so now I can find the speed and take the norm, take the magnitude of this guy. And I just sum the squares. So I get u squared plus 1 squared 1 plus 2u. And that looks great, right? How are people feeling? This feels wonderful. We all feel good about this, right? Because this is just square root of u plus 1 squared, which is u plus 1. Okay, whenever you can get rid of that square root in your speed, life is good, right? It's not going to be so bad. So we get rid of the square root and we feel good. And now we have a chance at calculating the arc length function. So now the arc length function, S of t, is going to be our integral from a starting point, our a, which in this case is 1, to t of our speed, which is u plus 1 du. And we all know how to integrate this. This is going to be u squared over 2 plus u, evaluated from t to 1. And so at the end of the day, we'll get t squared over 2 plus t minus 3/2. So this is what S is equal to. S is equal to this guy on the right. How do people feel? Now, we need to find the inverse function. What do you do? You go, huh? Swap? Swap the variables. Swap the variables. Maybe, but you gotta be smart when you swap. Let's multiply by 2. I like multiplying. It's something fun. T squared plus 2t minus 3. What you want is you want to solve for t in terms of s. You can solve for s in terms of t. I mean, if I give you a t, it's easy to get an s, right? If I give you t equals 5, you put 5 in, you get s. If I give you an s, what's t? That's what you want. So you go back to the Greeks, you talk with them, good conversation. Greeks will tell you how to do this. Probably in China, you could learn maybe a few thousand years before too. So they knew how to complete squares. So this is equal to t squared plus 2t plus 1. I added 1, I have to subtract 1, minus 4. Right? Which equals t plus 1 squared minus 4. Now I'll swap the order. So I get t plus 1 squared equals 2s plus 4, right? And then I know this t, it lives between 1 and 2. So this this guy is always going to, sorry, this guy is always going to be positive, so I can square root without an absolute value. And I will get t plus 1 is equal to the square root of 2s plus 4, or t is equal to square root 2s plus 4 minus 1. That's my inverse function. This is my t of, or s of t. So sometimes, as I said, sometimes it's not so easy to find inverse functions. And sometimes it's just like in closed form. Sometimes you know they exist, but there's not just a formula for them. I mean, think of the natural logarithm. There is a formula, but only after a lot of people studied it. And it's an integral. So we get an inverse function. And now, what do we do with that inverse function? Well, we just put it into our R. So we have R of S is equal to, pardon me, this is T of S, not S of T. Pardon me, this is R T of S, which is R of this nastiness. Let's just use our new computer skills here. And okay. And what is this? So how are we going to, okay, so can I leave it there? Is that okay? I mean, you just put that function in for each of these t's. Is that all right? Or do people want me to write it out? Is it okay? I'm not hearing any dissent. People look stunned. I can do it. I didn't hear any affirmation either, so I'll just do it. That's fine. So this is going to be, well, I've got a square of this thing, so but I really don't want to, so I'm not going to, because it will be ugly. So I'll just yeah, I'll just duplicate it. This is going to be a disaster. But you guys asked for it. Well, you didn't ask for it. You didn't do anything. So it's all my fault, right? I love this stuff. Give me some more room. Okay, so we just put this in. This is going to be 1/2 is this square. And then this is just what it is. And then I didn't give myself enough room. So I just take 2 times the square root of 2 over 3 times this to the 3/2. There we go. Done. How do people feel? Good. I saw one person nodding yes. So good. And you can see this is a parametrization in terms of S. It is not pretty, right? But you know, some things aren't pretty. I don't know, I didn't make the universe. So that's it. Now, why? Why do we want this? Well, and I'll just say this last part now. So one reason, of course, one reason is because you want to be able to have a nice parametrization of curves so that you can study them. But one of the things you can get out of such a parametrization of curves is curvature. So if we have a curve C is parametrized by arc length. In other words, it's arc length parametrized. R of S, then its curvature at S is written as kappa, which is equal to the unit vector at tangent vector at S, taking the derivative of that and taking the norm. you will notice that because it's arc length parametrized, this is also equal to the ordinary. The unit vector, because the speed is 1, the unit tangent vector is equal to the derivative, or this velocity vector. Pardon me, I'm sorry. Yeah, that's, I should say this. Okay, so what is strange about this? Well, and this is kind of a simple but an important point in physics, which is if you have, let me ask you, what is strange about this? What's strange about it is, what I'm saying is, if you take the derivative of the velocity, but at the same time, I'm saying that you're going at unit speed. So if you confuse those two notions, velocity and speed, this makes no sense. If I'm going at unit speed and I ask how much am I accelerating, derivative of velocity or if I ask the derivative of speed, well, you're going at unit speed, there's no change. However, velocities are vectors, right? So if I go in unit speed in a straight line, well, then I'm just, my direction vector of length 1, my unit direction vector is going to be constant. And so then taking the derivative of it will give me 0. However, if I'm going along a curve, even at unit speed, my velocity vector is changing. My unit tangent vector is changing, right? So I can think of it as being, my unit tangent vector as being on the unit circle, right? And, you know, well, let's see if I can get a vector here. It's not cooperating. There we go. So let's say we have a unit vector, and this is my velocity vector, or my unit tangent vector. If I'm going in a straight line, I'm just going in that direction. But if I'm curving, then it's moving, right? As I move along this curve, that unit vector starts changing. I get a change. And if I'm going at unit speed and I have a very sharp turn, then this thing is going to change very rapidly, right? It's going to go real quickly up here. And so what you're going to see is that change for very sharp curves is going to get very big, right? So you'll have a high curvature at that point. So I don't have quite enough time today, but maybe on Tuesday next week, what I want to do is just look at parametrize the circle with arc length and look at what the curvature of a circle is. And we'll see that it's very much reflective of the idea of curvature. Good luck on the exam tonight.